Hi, and welcome to Integration by Substitution. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. This comes to us from Chapter 4, Integration, Larson's 11th edition calculus text, 4.5, Integration by Substitution, and I've split this into two lectures. I don't like it when the videos get too long, so Part 1 is indefinite integrals, and Part 2 we'll look at definite integrals using substitution. First, the definition. Antidifferentiation of a composite function. Let g be a function whose range is an interval I, and let f be a function that is continuous on I. If g is differentiable on its domain, and capital F is an antiderivative of little f on I, then the integral, the integral of f evaluated at g of x times g prime of x dx is equal to capital F evaluated at g of x plus c. Letting u be g of x gives du equals g prime of x dx, and that comes to us from du dx equals g prime of x. Oh, my pen says nope. Treating these as differentials, I can multiply both sides by dx, and that's how I get this du equals. Previously, I've told you, remember, d dx is an operator. Well, we're looking at it now as a ratio of differentials. So du is g prime of x dx. That means the integral of f of u du equals capital F evaluated at u plus c. This is the opposite of the chain rule. So we don't have a product rule, we don't have a quotient rule, but we do have integration by substitution, which is the opposite of the chain rule. So if you need to, review composition of functions, the chain rule for derivatives, and my version of inside and outside in relation to composition. If you watch my video, I'll explain where I use inside and outside. Okay. So we're going to identify the inside, the outside, and the derivative of the inside in order to set up our integration. Looking at the antiderivative of 2x times the quantity x squared plus 1 to the fourth dx. Inside, when we think of inside, we're thinking inside of parentheses, inside of a radical, inside of a trig function, inside of a denominator sometimes, inside. So when I look at this, x squared plus 1 is inside the fourth power. So inside x squared plus 1, the outside is to the fourth. Once I identify my inside, I take the derivative. The derivative of x squared plus 1 is 2x. And we're going to call it 2x dx because it is the derivative based on the variable x. So here's what we're going to do in order to use integration by substitution. Let u be the inside, x squared plus 1. Then du is the derivative, 2x dx. I can rewrite, right? I'm multiplying all this together. Let's just throw that 2x at the end. The integral of x squared plus 1 to the fourth times 2x dx. X squared plus 1 to the fourth becomes u to the fourth. 2x dx becomes du. So I have my blue portion and I have my green portion, making my substitutions. I know that the antiderivative of u to the fourth is u to the fifth over 5 plus c. There's no limits of integration, I have to have a constant. Cool. I also know what u is. U is x squared plus 1. So if I start with x's, I want to finish with x's, I get x squared plus 1 to the fifth all over 5 plus c. Find the derivative here, and you will see that you're right. It's always nice to be able to check your answer, and that's how we'll check our answers. The integral of 3x squared times the square root of x cubed plus 1 dx. I look at x cubed plus 1 as the inside. It's inside a radical. And look at that. It has derivative 3x squared dx. 3x squared. My outside is the radical, the square root of something, or the 1/2 power. So let's let u be x cubed plus 1. Then du is 3x squared dx. The integral of 3x squared times the square root of x cubed plus 1 dx is u to the 1/2. Oh, what did I do that for? Wrong buttons. U to the 1/2 du. And I know that the antiderivative of u to the 1/2 is u to the 3/2 over 3/2. Indefinite integral always has a plus c. Dividing by 3/2 is multiplying by 2/3. 3/2 power is the square root of u cubed. I know what u is. U is x cubed plus 1. So that's the square root of x cubed plus 1 cubed plus c. Don't forget the c. If I'm looking at the integral of secant squared of x times the quantity tangent of x plus 3 dx, the inside is tangent of x plus 3. The derivative of tangent of x is secant squared of x. Derivative of 3 is 0, so secant squared x dx. There's really no outside. I mean, yeah, the parentheses indicate an inside-outside, but it's to the first power, so it's kind of boring. Let u be the tangent of x plus 3. Then du is secant squared x dx. Notice I'm not doing colors anymore. If you want to go back and check out the colors and maybe highlight them on your own, go ahead. But I don't think you need that. U is tangent of x plus 3. Du is the secant squared of x dx. Tangent of x plus 3 is u. Secant squared x dx is du. So everything's taken care of. The antiderivative of u is u squared over 2 plus c. Replace our u to go back to our x variable. I'll have tangent of x plus 3, the quantity squared, all over 2 plus c. Given x times the quantity x squared minus 5 to the 7th power, an integral with respect to x, my inside is x squared minus 5, so I'm going to let u be x squared minus 5. My outside is to the 7th power. I'll need that in a minute. My du, my derivative, is 2x dx, but I don't see a 2 up here. What we can do is divide both sides by 2 and get 1/2 du is x dx. Now, my x dx is replaced by the 1/2 du. My x squared minus 5 is replaced by the u. And I'll have 1/2 of the integral of u to the 7th du, which equals 1/2 u to the 8th over 8 plus c. Replace my u as x squared minus 5, and multiply my denominators. 2 times 8 gives me 16. What we're doing is taking something kind of difficult looking and making it simple. And I don't mean simpler, I mean simple. The integral of u to the 7th du at this point, you really should be on top of that power rule. That's u to the 8th over 8 plus c. Don't forget the c. Always a capital C in WebAssign. The integral of x squared times 2x cubed minus 1 all to the 3/2 dx. My inside is 2x cubed minus 1. Its derivative is 6x squared dx, but I don't have an extra 6 hanging out. So I take this equation and I divide both sides by 6. So 1/6 the du equals x squared dx. I will have my u value, u to the 3/2. I have my 1/6 du. My u didn't get highlighted very much there. I only have the x squared dx part, so the 1/6 has to come out in front. What is the antiderivative of u to the 3/2? It's u to the 5/2 over 5/2. Don't forget the 1/6 out in front of the integral. It keeps coming along. And the plus c, I write it at every stage so I don't forget it at the end. Dividing by 5/2 is multiplying by 2/5. Replace u with 2x cubed minus 1. And then I'm going to close this up a little bit. The 2 and the 6 simplify. So 2 over 30 simplifies to 1/15. 2x cubed minus 1 quantity to the 5/2 plus c is our solution. Inside, in this case the inside is inside parentheses, it's inside a denominator, there's a whole bunch going on here. I'm going to let u be 16 minus x cubed. Then my derivative is negative 3x squared. I go back up here. I don't have a negative 3 hanging out in the numerator. So I'm going to divide both sides of this equation by negative 3. I'll end up with negative 1/3 du equals x squared dx. So I take my function and denominator of 2, with an exponent of 2, gives me an outside function of something to the negative 2 power. 16 minus x cubed to the negative 2 power becomes u to the negative 2. This x squared dx is replaced by the negative 1/3 in the front and the du in the end. As long as it's all in there, it's all being multiplied, it's good. This negative 1/3, the antiderivative of u to the negative 2 is u to the negative 1 over negative 1. The negative 1 and the negative 1/3 makes a positive 1/3. U to the negative 1 is 1 over u. And after I get to this stage, don't forget the plus c. I do have the plus c there. That's 1 over 3 times 16 minus x cubed plus c. Find the derivative. If you don't believe me, take the derivative and you'll see that we did a good job. Let's do some trig functions. The integral of cosine of 8x dx. Well, the inside is 8x because it's inside of the trig function. The derivative is then 8. Derivative taking x. But I don't have an 8 up here in my integral anyway, an extra 8. I have an 8x, but I've already taken that up with u. So I don't have an extra 8 hanging out for my derivative. So 1/8 du equals dx, dividing both sides by 8. I can now rewrite the integral of cosine of 8x dx to be 1/8 the integral of cosine of u du. We've reduced it to an easier problem. We know the antiderivative of cosine of u is the sine of u, so this is 1/8 the sine of u plus c. And we'll go back and we'll put in our u value of 8x, find the derivative, verify that we are correct. The integral of sine of x divided by cosine cubed of x dx. In general, we can't create a denominator with very many of our derivatives, our du's. So if you have a denominator going on frequently, not always, but frequently, that will be our quote inside. That'll be our u value. So I'm going to let u be cosine of x, and its derivative is minus sine of x dx. The outside, third power in the denominator, so that's something to the negative 3 power. We're going to let u be cosine of x. Since du is negative sine of x dx, I can multiply both sides by a negative 1, because I don't happen to have a negative out here. Negative du equals sine of x dx, so sine of x dx is replaced by a negative du. Cosine of x to the negative 3 becomes u to the negative 3. Sine of x dx is turned into negative du. The antiderivative of u to the negative 3 is u to the negative 2 over negative 2, my negative sign from the front coming along. A couple of negatives here make a positive 2 in the denominator. U to the negative 2 is 1 over u squared plus c. After I take the antiderivative, notice this process when you're using the power rule. You've used these symbols, you've used them up in the process of finding the antiderivative, so you no longer write them. Just like after you let a limit go, when x approaches 3 and you substitute 3, you no longer write the limit. If you add 3 plus 4 and you get 7, we no longer necessarily write the addition symbol. So this is telling us to do a process. Once we've done that process, we don't have to write the symbols anymore. Replace our u is cosine, so this is 1 over 2 cosine squared of x plus c. Okay, a double substitution. I love these ones. But then again, I'm a math professor, so the integral of x times the square root of x plus 6 dx. There is absolutely no way we can simplify this as is. What do we have? We have an x plus 6 inside our parentheses. But what's the derivative of x plus 6? It's just 1 dx. The outside is the square root. But when I have u equals x plus 6 and du just equals dx, I have an extra x hanging out. So what we'll do, this is a double substitution. So I'm going to take my equation u equals x plus 6 and solve for x. X equals u minus 6. So right here, let's use blue, my x plus 6, that's my u. I'm going to use red. X equals u minus 6, taken up right there. And go for green, du equals dx. Yep, I need to underline this one. There we go. Making my substitutions. Now, what I have is, this is essentially just a change of variables, right? Substitution. But I've made it so now this square root isn't all jacked up and has an addition inside. This is something I can now distribute. U to the 1/2 times u is u to the 3/2. U to the 1/2 times a minus 6 is a minus 6 u to the 1/2. And I still have my du. I can do this. I can't do this. I don't have a product rule and things are weird, but I can do this. The antiderivative of u to the 3/2 is u to the 5/2 over 5/2, but we're going to, instead of dividing by 5/2, we multiply by 2/5. Minus 6 times. The integral of u to the 1/2 is u to the 3/2 over 3/2. So instead of dividing by 3/2, we'll multiply by 2/3. Minus 6 times 2/3 u to the 3/2 plus c. That's 2/5. I replace my u, x plus 6 to the 5/2 minus 6 times 2 is 12, divided by 3 makes a 4 as a coefficient, x plus 6 to the 3/2 plus c. Double substitution is a neat trick. When we can't simplify this, we can simplify down here. I know this is getting long, but I swear to you this is the last example. We have the integral of x plus 1, quantity, times the square root of 2 minus x dx. Again, we're going to have a double substitution, and one way to notice that is that neither the quote inside or the whatever this is have an exponent. So it's not like the derivative of the inside is going to take up whatever's left on the outside. So if they have the same exponents, a lot of times, not always, but a lot of times we're going to end up with a double substitution. Let's let u be 2 minus x inside that radical. Then the derivative of u is a minus dx. If u equals 2 minus x, I can add x, subtract u, x equals 2 minus u. So, the integral of x plus 1 times the square root of 2 minus x dx, exactly what we had, is the dx, that should be a minus du, right? I can just divide by minus 1 on both sides. X is replaced by 2 minus u. I'll still have my plus 1. This square root, that's the 1/2 power, and I know the stuff in green is just u, so that's u to the 1/2. So I have my dx is replaced by minus du. My x is replaced by 2 minus u. I leave the plus 1. My 2 minus x is replaced by u, and I still have my 1/2 power. Let's clean this up a little bit. This is 2 plus 1 is 3 minus u. Distribute the u to the 1/2. That'll be 3u to the 1/2 minus u to the 3/2. The negative sign out in front. So the antiderivative of 3u to the 1/2 is, add 1, I'll get 3/2 for my new exponent. Instead of dividing by 3/2, I multiplied by 2/3. I still have the negative sign. I still have the 3. The antiderivative of u to the 3/2 is u to the 5/2 over 5/2. This negative and this negative bring us a positive. Instead of dividing by 5/2, I multiplied by 2/5. U to the 5/2 plus c. Oh boy. Alright, so this one's negative, so I'm going to put it at the tail end. 2/5 u. U is 2 minus x to the 5/2. 3's cancel. This will be minus 2 u, 2 minus x to the 3/2 plus c. I know, that was a lot. Pause it, come back to it later, do what you need to do. Integration by substitution. This is the first part, just the indefinite integrals. Thank you for taking the time to listen.